Hello everyone, and welcome to our lecture on conflict serializability in database systems. This is part of our Database Fundamentals course where we explore the theory, design, and practice of database systems. Today we'll be diving into how database systems manage concurrent transactions while maintaining data consistency. Let's start by understanding the challenge we're facing. Modern database systems often execute multiple transactions concurrently. This concurrent execution brings several benefits. It improves throughput and resource utilization, reduces waiting time for users, and maximizes CPU and I/O parallelism. However, concurrent execution isn't without risks. When multiple transactions execute at the same time, they can interfere with each other, potentially leading to inconsistent database states. Our goal is to execute transactions concurrently while maintaining isolation, making it appear as if transactions execute one after another in a serial fashion, even though they're actually running in parallel. Serializability is our gold standard for concurrent transaction execution. Let's define some key terms. A serial schedule is one where transactions execute one after another with no overlap. This is the simplest form of execution, but doesn't take advantage of concurrency. A serializable schedule is a schedule that produces the same result as some serial schedule. In other words, even though transactions might overlap in time, the final result is as if they executed serially. To determine if a schedule is serializable, we have two main approaches: view serializability, which is based on reads and writes but is computationally expensive, and conflict serializability, which is based on conflicting operations and is much more practical. It's important to note that conflict serializability is a sufficient, but not necessary condition for serializability. It's a practical way to ensure correctness, even though it might be a bit conservative in some cases. Now let's understand what we mean by conflicts. Two operations conflict if they meet three conditions. They belong to different transactions, they operate on the same data item, and at least one of them is a write operation. Looking at the types of conflicts in our table, two read operations on the same data item don't conflict. This makes sense because reading doesn't change data. A read operation and a write operation on the same data item do conflict. This is known as a read-write conflict and can lead to dirty or unrepeatable reads. A write operation and a read operation on the same data item also conflict. This is a write-read conflict that can cause dirty reads. Two write operations on the same data item conflict as well. This is a write-write conflict that can result in lost updates. These conflicts are what we need to watch out for when analyzing schedules. Let's formally define conflict serializability. Two schedules are considered conflict equivalent if they involve the same transactions and operations, and every pair of conflicting operations is ordered the same way in both schedules. A schedule is conflict serializable if it is conflict equivalent to some serial schedule. In simpler terms, we're asking, can we transform the schedule into a serial schedule by swapping non-conflicting adjacent operations? If operations can be swapped to create a serial schedule without changing the order of conflicting operations, then the schedule is conflict serializable. When analyzing this schedule, we need to identify the conflicts. T1's read, B, and write, B, both conflict with T2's write, B. In both cases, T1's operations come after T2's operations. These conflicts create a precedence relationship where T2 must come before T1 in any equivalent serial schedule. Looking at the sequence of operations, we can see that this schedule is indeed conflict equivalent to the serial schedule T2 followed by T1. We could reorder the non-conflicting operations to get a completely serial execution without changing the outcome. Now let's look at a systematic way to test for conflict serializability: the precedence graph, also called a conflict graph. A precedence graph is a directed graph that represents the order constraints between transactions. The nodes of the graph are the transactions themselves. We draw an edge from transaction T to transaction Tj if an operation in T conflicts with and precedes an operation in Tj. The key test is this: a schedule is conflict serializable if and only if its precedence graph is acyclic, that is, it has no cycles. If there's a cycle in the graph, it means there's a circular dependency between transactions that prevents any valid serial execution. When the graph is acyclic, we can perform a topological sort of the graph to find a valid serial order for the transactions. Let's analyze our previous example using a precedence graph. Looking at the schedule, we identified these conflicts. T2's write, B, conflicts with T1's read, B, and T2's right, B, conflicts with T1's right, B. In both cases, T2's operation comes before T1's operation. This gives us a precedence graph with an edge from T2 to T1. Since this graph is acyclic, it has no cycles, we can conclude that the schedule is conflict serializable. The topological sort gives us the serial order T2 followed by T1. This confirms our earlier analysis and shows how the precedence graph provides a systematic way to check for conflict serializability. Here we can see a schedule with 3 transactions, T1, T2, and T3. The table lists their operations over time. Let's examine the schedule. We need to find conflicts. A conflict happens when 2 transactions access the same data. One operation is a write, and they are not in serial order. Here are the conflicts. First, T1 reads X at time 1, and T2 writes X at time 3. This creates an edge from T1 to T2. Second, T2 reads Y at time 4, and T3 writes Y at time 5. This creates an edge from T2 to T3. Third, T3 reads Z at time 2, and T1 writes Z at time 8. This creates an edge from T3 to T1. These edges suggest a cycle. A cycle means the schedule may not be conflict serializable. We will confirm this with a precedence graph on the next slide. This slide shows the precedence graph for our schedule, where nodes represent transactions and edges represent conflicts. A schedule is conflict serializable if this graph has no cycles. Since the graph has a cycle, the schedule isn't conflict serializable. In other words, it is not conflict equivalent to any serial schedule of the given transactions. To test for conflict serializability, follow this algorithm. First, identify conflicts between operations. Next, build the precedence graph. Then check for cycles in the graph. The time complexity is O of n squared, where n is the number of operations. Now here's how you implement it. First, create a node for each transaction. Then add edges for conflicting operations. After that, use depth-first search or breadth-first search to detect cycles. Finally, if there's no cycle, perform a topological sort to find a valid serial order. If you find a cycle, the schedule is not conflict serializable. Let's compare conflict serializability with view serializability. Conflict serializability is based on conflicting operations, while view serializability is based on reads and final writes. Conflict serializability is a sufficient but not necessary condition for serializability, while view serializability is a more general concept. The key practical difference is that conflict serializability can be efficiently tested in polynomial time, while testing for view serializability is NP-complete, making it computationally intractable for large schedules. This efficiency advantage makes conflict serializability much easier to implement in real database systems. Every conflict serializable schedule is also view serializable, but the reverse is not true. There are view serializable schedules that are not conflict serializable. Practical database systems implement concurrency control based on conflict serializability because it's efficiently enforceable, even though it might reject some valid schedules. Conflict serializability is what we call a conservative test. What does this mean? It may reject some schedules that are actually serializable, false negatives, but it never accepts a non-serializable schedule, no false positives. This conservative nature is actually a strength in database systems where data integrity and consistency are critical. The practical implications of this are, some concurrent executions might be unnecessarily serialized, potentially reducing concurrency, but we guarantee safety at the expense of some potential concurrency. The test is efficiently implementable in real-world systems. It forms the foundation for practical concurrency control protocols like two-phase locking. In database systems, we generally prefer to err on the side of caution rather than risk data inconsistency. Let's summarize the key points about conflict serializability. Conflict serializability ensures that concurrent transactions produce consistent results. Operations conflict if they access the same data item, belong to different transactions, and at least one is a write. Precedence graphs provide an efficient way to check for conflict serializability. A schedule is conflict serializable if and only if its precedence graph is acyclic. Conflict serializability is a conservative test. It may reject some valid schedules but never accepts invalid ones. It forms the theoretical foundation for practical concurrency control mechanisms in database systems. Understanding these concepts is essential for designing robust, concurrent database applications and for implementing effective concurrency control mechanisms. Thank you for attending this lecture on conflict serializability.